All right, well, let's see if we can get through what I want to get through today. And if we can, at the end, I'll ask you, or not ask you, I'll kind of do a summary of the solids of revolution. I know in my morning class I did have quite a few students who are still confused on when you subtract, when you add, how do you find that outer radius and inner radius. So I'll try and come up with some like generic sort of template for you, but it's time permitting, all right? We're gonna actually move on, and we're gonna talk about this topic it's actually in 7.2. At the end of 7.2, we've covered 7.2 with the exception of this, and we actually did 7.3 also, shells. And the reason why I'm coming back to this and doing this now is because this has nothing to do with solids of revolution, all right? So I figured if we did shells still is dealing with solids of revolution. This concept can kind of stand by itself on its own, all right? So there's really not like a technical name for this, but I'll call it something. This is solids with common cross sections. All right. Yeah. Okay. Solids with common cross sections. So let me take something that may be familiar to you. Let's say we take a cylinder and just take half of a cylinder. All right. So there's like half of a cylinder. See it? If I were to come in here and let me show you what this looks like from the top. Okay. From the top, it looks just like this, right? Just like a rectangle from looking straight down at this. If I were to come in here and make a cut right here, slice through it, it would be the same as cutting it through there, right? And if I cut that and I took that piece off and I looked at it from the side, what would it look like straight from the side? Like a rainbow. It would look like, you know, a little semicircle, right? Yeah? And no matter where I cut it, if I cut it further back and I took a look at that cross section, it would also be a semicircle, right? And for this particular solid, no matter where I cut it, right, as long as my cut is perpendicular to, let's say, this side, then every single cross section will look like this. So they all have a common cross section of a semicircle. Would you agree? That's kind of what we're going to do here with a slight exception. And that's our cross sections all have to look the same, like they all have to be semicircles, but they don't necessarily have to be the same size. Or maybe when I do a cross section, I don't get semicircles, I get something else. Like,
there was a problem like that.
Yeah, it's on the homework, and you probably couldn't do it because it was number 38 and 39. Yeah. So what if we had this like shoebox? Wouldn't it look exactly the same from the top as that other one did? But when I do my cross sections and cut, when I take a look, it's going to look like, well, that looks like a rectangle, doesn't it? Right? All the cross sections would be the same. So it doesn't have to be a semicircle. It could be a rectangle, could be a square, could be a triangle, could be a lot of different things. But the idea of this cross section, I'm trying to get that in your head first. Got it? Kind of understand? All right. So let's now take this region that's bounded by these two curves, right? And so we're talking about this region in here. And let's say that that is the base of a solid. Okay, so that's kind of like the ground. And what I want to do is I want to fill above this and create a solid. But here's what I want. I want the solid to be so that when I take cross sections like this and start cutting them, if I were to look at them from the side, they would be squares, but the length of the square, the length of each side, would actually be equal to the distance from the red function to the blue function. So like this. If I do this right here, draw that little, let's do like a little sliver. That look familiar to you? We've done slivers like that in the past, like a little rectangle there. Imagine that's a little cross section in here. When I look at it from the side, I want it to be a square. I don't like that. I want that to be a square. A little square slice. Does that make sense? So I cut from the top, I take that piece out, I look at it, that's what I see. But see, if I move my rectangle over, what's going to happen? I take that slice, what's it going to look like compared to that one? It's still going to be a square, but it's going to be bigger, isn't it? So I'm going to have a bigger square. That inner piece would be bigger. Something like that. Right? That's what that inner piece. And then what if I take a little slice off of this little rectangle right there? I'm going to have a little smaller little square over here, right? Get it? So the question is, if I were to make a solid that looks exactly like this, where cross sections form squares, with the length of each square being the distance between the two functions, what's the volume of that solid? What is its volume? Well, what we've done in the past when we had problems like this is we tried to come up with a formula, right, for a single one of these, and then we used the integral to add them up, right? So maybe we can generate a formula that would represent the volume of each of these slices. Now I want to show you, I want to use the computer to give you a better picture of what's happening here because I can only do so much on the board. So let's do it. Let's go ahead and lay this thing down on the ground. Okay. Oh, went too far. Okay, that's laying on the ground. Can you kind of see it? Maybe I should. Oh, I'm going to lose it. Okay, that good? Now, let's make some squares. So I'm going to make squares. And when I do that, so you see what's happened is I'm taking the distance from here to here. Actually, it doesn't look very proportional, but it's supposed to go up the same distance, over the same distance, down the same distance. And if I move this to like different slices, then you can see how that square changes shape. See it? Go to the middle, it's the biggest it's going to be. I go towards the other side, I'm going to get very, very small squares until I really get no square at the very end. Now if I put all these together, right? If I put all these together, all these little slivers, then I'm going to get a solid. And that solid, when filled in, would look like this. That would be the shape. And we want to know its volume. Get it? Yeah. I mean, there's some weird shaped buildings. Architects get crazy and they do things like this. Okay? Now, we could do squares. We could also do something else, like let's do those semicircles. So what I'm doing here is that I'm going to come in here. I'm going to say that this right here, this little rectangle on the bottom, right? From that, that's actually the diameter of my semicircle. And I'm going to just create a little semicircle out of this. So I've got something like this. Right? And then I do that. If I go further towards the middle, I'm going to have a larger semicircle, right? And the closer I get to the edges, the smaller the semicircle is going to be. Make sense? That should be a different shape than the one we just looked at, right? And it should have a different volume. Let's go ahead and see it. Now, unfortunately, I was trying to work on my code before I came to class. There's something in here I need to fix for semicircles. It's drawing the full circle, but imagine that it's cut off, like just cut this off at the bottom. Then do you see the half circle up there? Yeah? So as I move this thing around, as I move it through, the circle gets smaller towards the edges and then back towards that edge. So we get this shape right here. Definitely different than the last one, right? What's the volume of that? All right, we could do that. Maybe we could do equilateral triangles. Equilateral triangles are triangles that have all the same side, right? So what if I say I'm going to use this length right here as one length of the equilateral triangle and then form an equilateral triangle right above it and just create that little piece like that. Then as I get closer to the edges, the triangles get smaller, move towards the middle, it gets bigger, and we'd have this. So there's my triangle moving through. And if we put them all together, we get this shape. Do you understand the concept, the idea? Yes? Okay, so let's go with squares. We'll start with squares. I'm going to give us a specific example here. This is actually exactly what we're going to be finding the volume of, but I need to state the problem as if it would appear to you, all right? The way it would appear in like a book. So let's do it. Find the volume of the solid whose base is the region bounded by that's like a flyer gnat that's flying around up there, but it's showing up on here. Right. Find the volume of the solid whose base is the region bounded by y equals 1 minus x squared and y equals x squared minus 1. And cross sections perpendicular to the x-axis form squares. So this right here, what I'm going to underline, squares, that could change in the problem. We could change that to semicircles, we could change that to circles, we could change that to equilateral triangles. There's a lot of different things it can be. For this particular example, it's going to be squares. So we're going to start first by understanding the region that we're talking about that forms the base. And that's the region bounded by these two. And that's exactly what I just had up on the screen a second ago. So it really doesn't matter which one we color blue and which one we color red. But I'll just do this one. Which of the two functions is that one? This is y equals what? 1 minus x squared. And then the other one is the parabola that opens up. Comes something like this. This one is y equals x squared minus 1. So that's the base of the solid, right? Now, this next part is where we come in and we do that slice. So when we look at it from the top, we're going to slice straight down. So that's going to create our little infinitesimally thin slice. Okay, so we're taking like a deli slice out of a piece of meat, right? And we're just going to slice through it. And the important thing here is that it says cross sections, which is what I'm forming when I do a slice. I'm creating a cross section, right? My cross sections have to be perpendicular to the x-axis. So I could slice it this way, right? I could slice it like this. I could slice it any way I want, right? I could slice it like this. To be clear, we want to make sure you understand that the slices that we're making are perpendicular to the x-axis. Understand? That's why that wording is important. So cross sections perpendicular to the x-axis form squares. So when I slice that and pull it to the side, I should have a square. All right, so let's try and draw this same picture in three-dimensional space. So this might be one of your first experiences trying to draw something 3D like this. So whenever we try and draw 3D, always start with what we call the y-axis, which is just straight up. That usually is the sorry, did I say y-axis? I meant to say z-axis. This is the z-axis. Usually the straight up and down is the y, but what I'm going to do is I'm going to draw now an x, but not like an x that has 90-degree angles. It's going to be like a smashed down x, like this. And if you draw like that, then you get a pretty good idea of depth. Do you kind of see depth there? If you try and draw it like this, with a perfect, like 45-degree, like these are 90, right? That doesn't look three-dimensional, right? It looks like a snowflake or something, right? Yeah? Okay, so scrap that. We don't want that. Now what this is it's a representation of that where your x-axis is here, your y-axis here, and that's like the ground. And then you got the z-axis that's coming up. Do you all see it? Okay, now try and draw your parabolas in there. Now that's kind of tough, so I'm going to mark out like 1 unit this way, 1 unit this way, 1 unit this way, 1 unit this way. And now I'm going to try and draw my parabolas. The blue one is on top, so the blue one should be the one that's going like this, right? So I start here, I need to get to here with this thing that looks kind of parabolic. Then I got to go from here to here in this way, so it's kind of a tighter turn there like that. Do y'all kind of see that? Then I'm going to start with my red one. My red one's got to go from here to here, again kind of looking parabolic. And then from here to here, again kind of looking parabolic. So I think that's pretty damn good. What do you think? No? Damn's not a bad word. Hell's not a bad word, and damn's not a bad word. Just listen to the radio. I can get away with a lot of stuff these days. Right? Sure. It is. There's not much censored these days. It's hard to drive around with the radio on with my daughter in the car. Okay. You see it? And one of my students in my 9 a.m. class asked me and said, hey, on the test, do I need to draw this? And I said, yeah, why not? And, well, I'm not really good at drawing. I said, well, I wasn't good at drawing either when I was in your shoes, right? When I was in Cal 2, I couldn't draw in three-dimensional space like this. You have to practice. You get better, just like anything else. All right, now let's try and draw that little sliver on the ground, which is going to be, since it runs parallel to the the y-axis, right? That means when I draw it here, it's going to need to run parallel to this axis. So I'm going to draw my little rectangle in here like this. There it is. See it? And now I want to form a square, which means I need to go up, over, and down. Give it a little thickness to it. And there's my cross section. How does yours look? Pretty good? No? I think you need to smash your X down a little more.
I think I need to
Take art class? Okay, so this is an important drawing because what we're trying to get here is really just a formula for this slice, right? We want a formula for that single little slice. If I can figure out what the volume of this little piece is, then all I need to do is do an integral to add them all up. So imagine we're going to move this rectangle from here over, right? We're going to let x go from here to here across. That rectangle is going to change. As I do that, I build these squares up. These squares are going to change shape. So if I can find the volume formula for one of them, I integrate, I get the whole thing. Yeah? So, what is the volume? Well, length times width times height, right? Length times width times height. So we know how wide this thing is. How wide is that? Dx, okay. And do we know this length? Yeah, it's the distance between these two functions, which if you come back over here, was the top one minus the bottom one. So this should be the blue one minus the red one, right? I'm gonna kill that thing when it gets close enough to me. It's flying around, it's bothering me. So this one minus this one? Yeah? Y'all don't see it up here? No. You see it, right? Okay. All right, so top one minus bottom one. Tell me what that is. 1 minus x squared is the top one, right? Take away the bottom one, which is x squared minus 1. Now let's clean that up, because that's just algebra, right? What's 1 minus x squared minus 1? 2 minus 2x squared. Drop your parentheses, distribute the negative through, collect like terms. 2 minus 2x squared. That's how wide this is. But since these are squares, that's also how tall it is, right? So this side's 2 minus 2x squared. Any questions? No? All right, so what's the volume of this little sliver, this little slice, this little piece of bread?
2 minus 2x squared times 2 minus 2x squared times dx.
Yes, it's 2 minus 2x squared
Couldn't you just square it?
times itself again, so I'm just going to square it, right? And then just dx. That would be the volume of that little piece. And now add them up, right? Add them all together. And when we do that, we're going to bring the integral in. Okay, so integral time. I just erased the piece I need, but I think y'all can figure it out. The total volume, right? The total volume of the whole thing should be the integral from where to where. We didn't get those points of intersection. We didn't figure out where these were, but I thought they were obvious. Were they obvious? 1? Negative 1 and 1? Okay, you just get that by setting these equal to each other. Or just like look at it and be like, okay, yeah, negative 1 and 1 work, whatever. Either way, you could get that, right? Negative 1 to 1. And then use this formula right here for each slice. So 2 minus 2x squared, that quantity squared, dx. And we're in business. All we'd have to do is square that out, collect like terms, integrate, plug in, and we're done. So dot, 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 right? You could figure out the rest of that. Questions? Is that pretty straightforward? All right, let's change the problem. Let's do, instead of squares, let's do circles. Let's do full circles. Okay. Now I have to be a little bit clear, more specific in this. Circles. The diameter is in the xy plane. In other words, I'm telling you right there that the diameter of that circle is always the part that's on the flat piece, on the ground. So that's where you determine how long or wide the circle is. All right, so I'm actually going to draw this all again. I think it'll be a little faster this time. Blue on top, red on the bottom, and then over here, and draw it again. Let's get a little more practice. Go a little faster though. Oh wow, I missed. Forgot what I was doing. Okay, this has got to go through at the same place. Over here it's got to go through at the same place. All right. Good enough. So I've got circles, right? So I've got this little slice in here. It's got a little thickness to it there. That's this slice in here. And now that's the diameter, right? The diameter of this circle is in the xy plane. So that's my diameter of my circle. So if I draw a circle with that diameter, I get something like this. And it's hard to see because that's all cluttered up there. So it's easier to come, I think, over here to draw your circle. Just draw a circle, give it some thickness like this. Good enough. Now what we know about this circle is that if you were to look at the actual distance across, right? That distance across is equivalent to this distance, which is equivalent to this distance, isn't it? Right, from here to here. So what is the diameter of this circle? The diameter of this circle is what? It's going to be the blue one minus the red one again, right? Which we already did that algebra, didn't we? This is 2 minus 2x squared. Agreed? That's the diameter. I don't need the parentheses. I'm not sure why I did that. Agreed? Huh? No, this is the whole thing. This is the whole thing. So that's the diameter. Now, what is the volume of this? That's a cylinder, isn't it? Pi r squared times height. Well, we know what the height is. The height's really kind of just the width of this, which is dx. So I just need pi r squared.
R is half of that.
Yeah, the radius is half of the diameter. So the radius of this circle is half of that. Just distribute a half through, so you just get 1 minus x squared. Agree? Questions? So the volume of this little piece is equal to pi times your radius squared dx times the height dx. Pi r squared times height. That will give me the volume of one little slice. I just need to add them all up now. So the volume of this solid with this particular cross section of circles will be the integral -1 to 1 again. And then it'll be pi, which I can pull out of the integral, right? Because it's a constant. And then 1 minus x squared dx. Okay. What if we did semicircles instead? Just half of this answer, right? You could just do this whole thing again and just put a half anywhere you want. You could just throw the half right in here, right? Because that's the volume of the full cylinder. You want half of that, so you just put a half. So there's not a big difference in the formulas from circles to semicircles.
Could you wait till the end?
Mm-hmm.
Could you wait till the end?
Yes, you could. All right, let's do one more. Let's do equilateral triangles. What is an equilateral triangle? All sides equal. So I'm going to see if I can do this one by just drawing the sliver. Is that all right? Can I just draw the slice? Everything else is the same. So we have the rectangle that was on the ground, like this, and I create an equilateral triangle from that, like this, roughly. We know that this side right here should be what? 2 minus 2x squared. We've done that already. In fact, all the sides are that, right? So what is the volume of this thing? The volume should be the width of it, right, which is dx, right? That's in there. Let me throw that on the end. But the other piece, that other piece that we're missing, is the area of the triangle. Because all you do to get the volume is you find the area of the triangle and you multiply it by how thick it is. So what is the area of that triangle? And that's not a simple problem. Is it what? Sine squared what? The side squared. Let me draw you that triangle. Just looking at it, you know, straight on, if we were looking at it straight on, not considering the thickness at all. If this side's 2 minus 2x squared, this side's 2 minus 2x squared, this side's 2 minus 2x squared, can you tell me what the area of that is? Ooh. Do you remember ever in pre-cal finding the area of a circle if you had all three sides? Law of cosines, the problem with law of cosines is that within the law of cosines there's an angle in there also. There's a formula, it's nasty, it's called Heron's formula. I actually could not remember that at 9 a.m. this morning. I couldn't remember the name of this formula, but I remember it now. So it's called Heron's formula. It's a disaster. We're not going to use it, all right? But there is a formula you can use. It's rather complicated, where if you have three sides of a triangle, and it doesn't even have to be equilateral, any triangle, then you can find the area using that formula. I'm going to use something else, though. I'm going to use this good old formula. So I need to, this is kind of a little bit of a review of pre-cal, and not even a review, it's just kind of like, you might have got through pre-cal without this, who knows. If somebody gives you a triangle, and it does not have to be a right triangle, if somebody gives you a triangle, if you know the height of this triangle, and you know the base of the triangle, which is this side, then I think we're all comfortable with this formula. Area is 1/2 base times height. Right? Seen that before? You're okay with that? All right. Anybody know where that formula comes from? Not really? I'll show it to you. It's pretty cool. Take this, okay? Right-click copy, okay? So we make a copy of it. Now right-click paste, and throw another one down here. And I want you to turn it over. Rotate it like that. Okay? Yeah, you see that? That's a copy of this. All I did was just turned it like that. Okay? See it? So that's two of them, right? Now, you see where it's cut here? Take that piece, take it off the piece of paper and stick it right here instead. And now that's gone, right? And what do you have now? That's going to be a rectangle, right? This is height, and then this right here, well, this side right here is base still, here to here. So if I do base times height, that gives me the area of the whole thing, but this was actually two of them, wasn't it? So half that and you get the formula. Okay, it's not important. So that's our formula. That's our classic formula for the area of a triangle. What's wrong with this formula? Why can't we use this right now? We don't know the height, do we? We don't know the height. The height would be this distance right here. Now, could we get it? Yes, we could. There would be some work. We could form a right triangle. We could just look at half of this. We could use Pythagorean's identity. We could do it, but it's too much algebra. There's another formula for area of a triangle that you should know. All right? Anybody know what it is? No? Just curious. All right. Here's the way it works. I'm going to add a couple of pieces to this triangle. I'm going to call this side A and this side C. Remember with triangles, we usually call them like A, B, C for the different sides? I'm going to call this angle right here theta. Now notice that is the angle between A and B. The area of this triangle is equal to 1/2 A times B times sine of theta. Does that at all look familiar? No? Yeah. Okay, so look at this formula. This formula usually freaks students out. They're like, where in the world did this come from? Because this looks kind of crazy, doesn't it? But I can show you how simple this formula is to derive. Take this right here in red. What type of triangle is this? Right triangle. Just tell me, in terms of all the letters we have there, what's sine of theta off that red triangle? Sine of theta is, it's opposite over hypotenuse, right? So h over a. Please solve that for h. Solve for h, and what do you get? A sine theta is h. Agree? Now come back over to this formula that everyone loves and replace h with a sine theta. And what do you get? You get this. You see? So this formula, the power of this formula is that you don't need to know the height. What you need to know, though, are two of the sides and the angle between them. And for our particular triangle, do we know two of the sides? Well, we know all three, right? But we know two of them. Do we know the angle between them? 60 degrees. It's an equilateral triangle, right? So this is 60 degrees. So I can come up with the formula for that pretty easy using this formula. Got it? So I still need to come back up here and get that, but I'm continuing my thought over here. The area of this, pardon? Yeah, we're just going to tag the dx on the end. So really what I'm trying to find is the fill in the blank part right here. And so the area of this triangle is the fill in the blank part. The area should be 1/2 a times b, which is this side times this side. So 2 minus 2x squared squared, right? Then sine of 60 degrees. What's sine of 60 degrees? Sine of 60 degrees. 60 degrees, what's the y coordinate at 60 degrees? Root 3 over 2. Sine of 60? $60 degrees, what's the y coordinate there? Root 3 over 2. And so this I can rewrite as root 3 over 4, 2 minus 2x squared squared. I just brought the 3/2, root 3 over 2 up here to the half. And that's it, right? That's the area of that triangle. So when I come back over here and I want to know the volume of this little cutout that we made, I just needed to know the area of this times the thickness. I had the thickness, dx. The area is just that formula right there. So root 3 over 4, 2 minus 2x squared squared.
So for other triangles are not square, would it always be square root 3 over 4?
For other triangles, if it's an equilateral triangle, yes, it'll always be,
Other equilateral triangles,
yes.
was my word. All we would change would be the middle complement, like the 2 minus 2x squared.
Yes, that's the part that's going to vary. The question was, you know, if we have another problem that's given to us and we're asked to find equilateral triangles, like what part of it's going to change? The only thing that's going to change is the subtraction of the two functions. You're always going to have the root 3 over 2 because you're always going to have 60 degrees on an equilateral triangle. And you'll always have the 1/2 because, well, the formula has a 1/2 in it. It's this piece right here that'll change.
Will there be a case where it's not an equilateral triangle?
I won't give you something other than an equilateral triangle, but you could do like an isosceles triangle. Isosceles would be something like where two sides are the same, maybe like this, but that side's not. But if someone gave you that, they would have to tell you what the relationship between this side and these sides are. So maybe whatever this is, these sides are twice as long or something like that. You would have to be given that relationship. I won't do that to you. The book doesn't do it to you. I'm not going to do that to you. But even in that event, we could still use that formula because we know two sides and we could get the angle using properties of triangles and stuff. Okay. Fun stuff. Let's now get our final formula. What is the volume of the whole solid? Integral, right? Do we have any constants we can pull out? Root 3 over 4 can come out. And then we have the 2 minus 2x squared, that quantity squared dx. I forgot my negative 1 to 1. Done. And that's it. That's that last little topic. So the homework assignment that I put on the board last time, there was problem 38 and 39. Those two you really theoretically couldn't do. So now with this, you should be able to go finish those off. And we're ready to move on. Supposed to be crazy weather this evening, right? That's what I'm hearing. Pardon me? Oh yeah, it's going to be like late at night. That's
Yeah, it doesn't show up like on my phone.
yeah. Maybe they'll cancel school tomorrow.
I used to YouTube. I have an exam in my intro to programming class tomorrow morning at 9 a.m.
All right, we're ready to move on. 7-4. I don't know if any of y'all have noticed, but this is pretty much the point in the class where my lecture notes online no longer appear. Like there aren't any more lecture notes online. And it's really because of the nature of what we're going to do now. There's not a whole lot of notes that need to be put up. So, I might provide you with some resources, but I'll just hand them out in class. This, as you'll see, isn't going to require much, all right? We're going to come up with this concept of what's called arc length. And remember, the underlying theme of this entire chapter so far has been using the integral to add up things, right? And the integral, we just need the integrand, the part inside, is just the formula for what we want to add up, right? Whether it be areas or volumes of solids or shells or cross sections of some weird solid, right? All of it's just a formula inside. So arc length. Let's just take a function, just your regular old function of x here. Back in college algebra or calculus 1, we've got some functions sitting on a piece of paper. And what we're interested in here is if we could take this thing off the page. So imagine that this was like a rope, okay? And I could take it off the page and straighten it out, right? Can I borrow your charger cable?
It's a little broken.
That's okay. I'll break it some more. That's all right, though?
Yeah.
Okay. So if we had this right here and we were able to somehow take this frayed fire waiting to happen cable, right, and take it off the page and then straighten it out and measure it, then, how long would that be? That's the arc length. Pretty simple concept, right? Yes? The idea of what we're trying to do, that's pretty straightforward. So our question is, how long is that? Well, one thing we could do, right? One thing we could do is we could approximate it. We could imagine creating a right triangle here, connecting these 2 points with a hypotenuse. And that hypotenuse would be an approximation. We would be way off though, right? Yeah? So how could I get a better approximation?
Could you break it up into 2 parts?
Yeah, why don't instead of me using one triangle, why don't I cut this thing, okay, cut it into 2 equal sections, do this triangle, and then do a little triangle right there. Do y'all see how that's probably going to be a better approximation? Or no, you're not happy with it? Well, it's not a triangle unless you extend it over, then it would be a right triangle, right? I could get that to be a triangle. Yes, I agree it's not. It's a trapezoid or something, but you get the idea? Okay. And then I could try and go even better by maybe 3 or 4. Maybe I do, a couple of these and start connecting here to here, and then 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 here to here. And each one of those, I could create little right triangles on each one of them. Yes? Okay, and then wherever that one would be, I don't know. And then here's a little right triangle in there, and there's a little right triangle. So if I were to get all the hypotenusi, what is the plural of hypotenuses? Hypotenuses? Hypotenuse? I don't know. Get the hypotenuse of each one of those, right? Add them up, and that would be a better approximation than that one, wouldn't it?
Yeah.
And what would be the exact arc length? If I cut this up into an infinite number of them, right? And that's exactly what we were doing when we were doing areas, right? We were coming up with infinite cuts. So really, I need a formula that represents the hypotenuse of one slice, okay? Just the hypotenuse of one slice, and that's what I'm going to try and create here. All right, so let's start over here. Go back to this. Start this thing over. I mean, the integral is amazing in this way. If you can just come up with a formula for what you're trying to represent, then you can add up all these pieces. So I'm going to take some arbitrary slice. So a slice means I need some sort of width here, which would probably be called, I don't know, dx, right? And go up here. That'll hit 2 points, and I'll create a little right triangle out of that. And, well, that's too hard to see, so let's just blow that thing up, okay? Let's just zoom in on that and take a look at what we've got here. We've got some curve doing something in here. We've got a right triangle that we've created, and the hypotenuse that is right here. And yes, there's some error, but as I let this thing go to the width of this become infinitesimally small, the error basically vanishes away to 0. Now, when we have right triangles, we like Pythagorean identity, right? And we know already how wide this is. This is dx, right? We don't know the hypotenuse, but we want to know it. This side right here is actually dy. If this is the infinitesimal change in x, then this is the infinitesimal change in y. As you go from this point to this point, this is how much your x changes, this is how much your y changes, right? And if I know two sides, then I can automatically get the third. This squared plus this squared must be this squared, right?
Yeah.
Or this is the square root of dx squared plus dy squared. That's the length of that, isn't it? And I just need to add these up. The problem right now, as you might suspect, is that if I do an integral right now, it's going to start at A, it's going to end at B. That's pretty natural, right? We've been doing that. It'll go from A to B, but this formula, there's something that should be glaring at you, and you're like, whoa, we've never seen this before. What is the problem? What is that? Sorry? The dx squared. Yeah, hasn't every single integral we've done in this class had dx sitting out here? And this does not have dx sitting out here. And so that is a major issue. We need to resolve that. And it's going to be easy to do, but I need you to go back to Cal 1 and just think about something for a minute. All right? I mean, the setup is pretty straightforward though, right? Create this little infinitesimal right triangle, figure out its hypotenuse. So recall from Cal 1 some notation we had. If y is a function of x, then when we wrote f prime of x, we had another notation called Leibniz notation, which said that we would write that as dy dx, right?
Yeah.
And I would like you to, I'm going to try and replace this dy right here. So I'd like for you to take that equation and solve it for dy. So just multiply both sides of this equation by this little dx, which we call the differential of x. So you're basically going dx here and dx over here. So you'll get f prime of x dx equals dy, right? All right, let's go back to this. let's rewrite this, replacing dy with that. Okay? So we needed that, but now we're going back to this formula. So this right here equals the square root of dx squared plus what? F prime of x times dx squared. Yeah? Now, if you have two things multiplying and then you're squaring them, you can square each one, can't you? So this is going to become square root dx squared plus, let me write it this way, f prime of x squared times dx squared. So I'm just squaring each of these factors. And I just chose to use brackets so that I wouldn't get like parenthesis crazy here. All right? Now what do both of these have in common? They both have a dx squared, right? This term has a dx squared. This term has a dx squared. Factor out a dx squared. You get dx squared out front here. Then you'll have what? You got to be able to get that back. So 1, right? Plus, and then this thing, f prime of x, that quantity squared. That is what happens when you factor a dx squared out. Yeah? And because that's multiplication, you can split this into two roots. And what would the square root of dx squared be? Just dx. So we're going to get the dx to pop out. And this turns into square root 1 plus the first derivative squared. And then the dx, instead of putting it out front, I'm just going to put it back here because, well, it's about to go into an integral, isn't it? So we'll just usually put that dx out back. And that's it. That's our formula. So the length, if you like formulas, we have a nice formula for arc length. The length of a curve will be equal to the integral from a to b of the square root of 1 plus the derivative of the function itself, that quantity squared dx. There's your arc length formula. So it's a nice formula, but it's got some problems. We've seen in this class how challenging it can be to integrate square roots of things. In fact, we had an entire section called trigonometric substitutions, which helped us deal with square roots of certain forms. So this inherently is usually a difficult thing to compute, all right? It is usually difficult. Someone give me a function, just a common function. Like something, the first thing pops off the top of your head. What is that? What? X squared. I could probably do that. Find the length of it. Yeah, well, I don't know. It might be tough. X cubed would be tough, I think. Sin x would be tough. There would be a lot. So my point is this. As the next examples I'm about to give you had to be very carefully chosen so that once you create this integral, you're actually able to do it. In general, it's not that easy to get these. So this is where we would use a computer to run an algorithm to get the length. But the computer needs series, and that's chapter 8, and we haven't talked about that. So, all right, you ready to find the length of a curve? All right. Y'all seem just overjoyed. All right, we start out easy. All right, let's find the length of f of x equals x to the 3/2 on the interval 0, 1. So we could have we could graph this on our graphing calculators and we would see what it looks like and, whatever. But we just want to find its length. And we don't need to draw any pictures, okay? For arc length, no pictures need to be drawn. You just can go straight to the formula. So what things will we need to do this?
Square root of 1 plus the derivative.
Square root of 1 plus the derivative squared, right? So why don't we just get the derivative first? Let's do some work first, then we'll go write the formula down. So what is f prime of x? We need that, right? This is derivative, not antiderivative, right? That's the good old power rule. Drop the 3 halves out front, subtract 1. That's your derivative. Now, within my formula, I need to square that, don't I? So we may as well square it now. If I take this and I square it, I get 9/4 x. Right? Because when you square, that 1/2 is square root. So when you square the square root, it goes away. All right. I think I'm ready. I think I'm ready to kind of go to the formula now and see what happens. The length of this curve should be the integral from 0 to 1, okay, square root of 1 plus the derivative squared, which I already did that work, dx. And now the question is, can you integrate that?
Yep.
How would you integrate that? So I'm going to do that over here. I'm going to write it down as an indefinite integral and act like I'm back in chapter 6 now. Actually, I don't even need chapter 6. How would you integrate this? Basic U sub. This is the good old, do you see something in its derivative? What's the U? 1 plus 9/4 x. Just grab the whole thing underneath the root. What's the derivative of that? 9/4. Just 9/4 dx. You don't have a 9/4, do you? But you have a dx, so I can get rid of this, scale it out, multiply both sides by 4/9. And now rewrite the integral. So if I rewrite this integral in terms of u now, it will be integral, let's see, this is square root of u. I'm going to write that as u to the half. And then what's dx? 4/9 du. So how about 4/9 out here? du. And we can integrate that, power rule, right? So this will be 4/9 times, add 1 to that, we get what, 3/2. So we put a 2/3 out front, u to the 3/2, plus some constant. So it's looking like, 8/27 u, which is all of this, to the 3/2. Yeah? That's our antiderivative. Questions? So I'm coming back over here now. I'm ready to finish this off. This will be 8/27 and then 1 plus 9/4 x to the 3/2 evaluated from 0 to 1. So that's the way we do definite integrals, right? You find the antiderivative, then you plug in the bar over here, and then you're going to go and plug in 1, then 0, subtract, and be done. Yuck. Let's plug it in. Who cares, right? Plug in 1, 9/4. What's 9/4 plus 1? 13/4. So I'm just going to write this down. I've got 8/27. Then I've got 13/4 to the 3/2, right? That's what I have when I plug in 1, which is a number, right? It's ugly, but it's a number. Then minus, what happens when I plug in 0? You just get 1 to the 3/2, which is just 1 times 8/27. So how about just 8/27s here? And I'm going to box this and leave this as my exact answer. And I would take that on a test as full credit. I don't need the decimal. I prefer it to be in its exact form. Now, it would be interesting to see what that is as a decimal, because then you would have some idea, like, you know, if it's like 1.756 or something like that, you have some idea of how long that thing is. Now, this, I mean, why would you ever need an arc length, right? I mean, it's kind of strange, but see, in Cal 3, what we do is we extend this out. Like right now, this is a curve on a flat sheet of paper, right? But imagine that you can take this concept and extend it out into three-dimensional space. So like that little gnat that was flying around, or mosquito, or whatever that thing was that was bothering me a little while ago, like it's flying around the room and it's tracing out a path in the room, isn't it? And if we were to keep track of where it is and watch it go through and then, you know, it lands, we could take that path and imagine straightening it out, and we could figure out its linear distance that it traveled through that path. Or you could, you know, it could be a rocket, or it could be an airplane, it could be a...
Make a function out of
they're called vector functions, curve functions.
slides or flying around randomly?
Well, no, you would have to somehow gather that data, but, you know, anything that's flying through the air, there's going to be some function that would match its flight, so to speak. And once you have that function, then you can do a lot of stuff with it. All right? So this is just the two-dimensional case. Later on, you go to three-dimensional. Let's do something a little harder. This next problem always seems to find its way onto my test. I'm not quite sure why. It just always, I just enjoy the next type of problem. Okay, x to the fourth over 16 plus 1 over 2x squared. Let me double check that. Yes. Remember, I said these have to be picked very special in order for them to work. Now that's a pretty nasty looking function, right? But it's going to work out beautifully in the end. So I'm just going to first remind you of what this function is, written a little differently. Isn't that the same? Okay. I did that because it's going to be a little bit easier for me to take the derivative if I rewrite it that way. So what is the derivative of, why am I taking the derivative? Because the formula needs the derivative, right? Squared. So I'm taking derivative. What is the derivative of this? 4/16, which is the same as 1/4, right? X to the third. Then? Minus x to the -3. So power comes out, subtract 1 from the power. That's where we are. I need to square this, don't I? Before I square it, let's all agree with this. That's this, right? I'm going to drop that negative exponent, I'm going to drop it down. That's what the derivative is. And let's square. Well, that would be just this times itself. Right? That's what that means to square it. And now you can expand it or FOIL it if you like that instead. What's my first multiplication give me? 1/16 x to the 6th. Next multiplication, be careful here. Close. 1/4 is right. Negative 1/4. Minus 1. What happened to the x cubes? They canceled, right? And a negative times a positive, that's going to give you negative. So we get negative 1/4 on that multiplication. What do we get on the inner multiplication here? Minus 1/4 again. Y'all see the x cubes canceling? Yes? How about my last multiplication here?
Plus 1 to the x.
Plus 1 over x to the 6th. Which I could clean this up a little and say 1/16 x to the 6th minus a half plus 1 over x to the 6th. I just put the 2/4 together. All right, so that's my derivative squared. Yeah? I think I'm ready to go to the formula. I think I am, I'm not sure. That was all just my work to get me to this point. The length of this curve should be the integral from 1 to 2. Why is it 1 to 2? That's what I told you, right? I told you it was from 1 to 2. Square root 1 plus that. 1/16 x to the 6th minus a half plus 1 over x to the 6th dx. Can you clean that up at all? Or do anything with that? You can combine some like terms, can't you? That 1 that you have minus the half. Right? 1 minus a half is a half. Now, normally, if you saw something like that, you should get a little bit ill. Like you should feel a little sick if you see something like that, because that's not an easy integral. If the square root wasn't there, would it be easy? Yes, but the square root is there, so that is definitely no go. The only thing we've had with square roots that have saved us is like the previous problem we did basic u sub. No, right? No basic u sub here. Trigonometric substitution, but for that we needed something like a squared minus x squared, or we needed x squared minus a squared, or we needed like x squared plus a squared, right? That's what we needed. We don't have that, do we? So, any ideas? Split into 3 different roots. Can you do that? Is that a legal algebraic move? Why can't you split up roots like that? Yeah, like if I had this, why can I not do this? Because it's locked in? Well, if you ever forget that you can't do that, just think about it for a second. This right here is 13s, right? So this is root 13. If you think that this is true, then this should be 2 plus 3, which is 5, right? So is the square root of 13 5? No, then I must have messed up. Do you see what I'm saying? You can always go back and check yourself. So splitting into 3, no go.
Integration by parts.
Ooh, okay, integration by parts. What are you going to choose as your u and your dv?
I would choose u as the left equation, the square root of and all that under, and then for dv dx.
Okay, so you want to make that your u and this your dv, and then when you differentiate that, enjoy. That's going to be nasty, right?
Yeah.
And then when you integrate that, you'll get an x. So I don't know, maybe, but I don't see it getting easier. I see it getting more complicated that way. But you're taking a swing. I mean, that's what you have to do here. You have to take swings at this. I'll give you a hint. There's no technique of integration that you need. You actually need to do some algebra right now. Okay, completing the square, that's what my other class wanted to do also. Try and complete the square. The only issue that I see with completing the square is that normally that works great with like quadratics. And this isn't really a quadratic. So maybe, can we hold off? Maybe we can find something else before?
That's factoring.
How do you mean factor?
You do, I haven't totally worked this out, but I think like if you do 1/4 x to the third plus x to the negative third.
Wait, 1/4, what? Say again? 1/4?
X to the third plus x to the negative third.
that's going to work. I'm not quite sure everyone's going to see that. Okay, that is correct, but you can see it. We got to get to that. So that's very good. Give me anything that you, like, anytime you've seen a bunch of fractions together, anything that you could do to, like, make your life a little better sometimes. Combine them together? Common denominator? Let's just see what happens if we get a common denominator here. So do you all understand that we're kind of hung up on this part right here? That's pretty nasty looking. So I'm going to come over here, a little bit of scratch work. I'm just going to mess with that part in the blue. 1/2 plus 1/16 x squared, or x to the 6th, sorry. And then plus 1 over x to the 6th. Find me a common denominator. What would a common denominator be here? 16 x to the 6th. 6th, right? 16x to the 6th. So what would I need to multiply on the top and bottom of this fraction to get that? 8x to the 6th here, 8x to the 6th here. That would give me the common denominator of 16x to the 6th. How about this next one? And be careful, because this x to the 6th is actually up top, isn't it? So what would I need down there? Top and bottom. X to the 6th on the bottom and the top. Do y'all see what I'm doing? How about the last one? What? 16, 16. Okay? Y'all see what I did? All right. Now, put these together. What's the new numerator right there? 8x to the 6th. What's the new numerator here? X to the 12th. What's the new numerator here? 16. All over the common denominator. Okay. Now, here, let me arrange this in descending order on top. Now I don't have any fractions. And I'm hoping that at this point, it's a little more obvious that the numerator is something very special. It's two things multiplied together. You can factor the top. What does the top factor to be? X to the 6th plus 4, and then x to the 6th plus 4 again. Do you see that? This times this will give you x to the 12th. This times this, 4x to the 6th. This times this, 4x to the 6th again. That gives you 8 of them. 4 times 4 is 16. Agree with that? And then this is x to the 6th plus 4 squared over 16x to the 6th. Laura, I know that's not what you did, but it's the same. It's going to give us the same thing at the end. Yes.
You said this problem is on the test usually. All this.
This is always, yes. I mean, I almost without fail put this on the test because this is algebra that you all need to know how to do. Be expecting it. That's the thing. You should expect to have to do this sort of algebra on the test. All right? Good? Now, why am I excited about that being in there instead of that? What am I happy about? This is going to go right here, right? Yeah, when I take the square root of this, if I take the square root of the top, the square is going to go away, right? And the square root of the bottom is pretty straightforward. Yeah? So let me continue. So I have equals integral 1 to 2 square root of this thing, x to the 6th plus 4, and then 2, and then 16 x to the 6th dx. Now go ahead and take the root on the top and bottom. The root of the top is just x to the 6th plus 4. The root of the bottom is 4x what? I've heard fourth and third. Third. When you square x cubed, you get x to the sixth. Right? Power to a power, you multiply the powers. Questions? I'm happy. There's no more root, right? It's good. How would you integrate that? You could split that into two integrals, couldn't you? You could go integral 1 to 2, two things here. You can go this over this over this, right? So what's x to the sixth over 4x cubed? X to the third, right? With a 1/4 out in front of it. And then what's the last one? 4 over 4x to the third. It's just plus x to the negative 3. So Laura, you saw that from this to here. That's really good. All right. You could integrate that, right? I mean, term by term, antiderivative of that, antiderivative of that. Power rule, pretty clean. Yeah. Equals dot, dot, dot. So I'm going to stop there. All right. You all happy? All right, got about 22, 23 more minutes. Next problem, I hope you'll enjoy. Do you remember that problem I did a while back when we were doing areas? Didn't I prove to you that the area of a circle was pi r squared? Do you remember me doing that? Y'all were all excited, or like throwing confetti at me at the end. Do you remember that? That's the way I remember it. Okay, so here's what I'm going to do. I'm going to go back to the good old circle. And I'm going to throw a formula up here that we've all seen. Circumference. The circumference of a circle is 2 pi r. Why? Because that's what you've been told, right? Now I'm going to show you where it comes from. So what we'll do in order to do this is we're going to imagine that we orient this circle at the origin like this. And then, do you remember we had to come up with the equation of a circle? And the equation of this was x squared plus y squared equals r squared. And we went as far as even solving that for y. And we said that y would be equal to square root r squared minus x squared. In fact, it's actually plus or minus. The positive root of this would draw the top half of the circle. The negative root would draw the bottom half. Does this ring a bell? Yeah? You all can respond. It is okay. Do you recall it or not? Yes. Yes? Okay, thank you. So, what I'm going to do, see if I can convince you of this. I'm just going to look at this first little quarter of the circle right there. I know that I can draw that piece of the circle using the function f of x is equal to this. And I can do that on this interval, bless you, 0 to, what is that? 0 to what? 0 to what? I think I heard it. R. 0 to r. So if it was the unit circle, yes, it would be 1, but we're doing an arbitrary radius, okay? That's why this is important in the problem. Okay, do y'all understand? I can draw that curve, that blue curve, as long as I do this function on that interval. So why don't I find the arc length of that function then? And wouldn't that give me the length of that little quarter circle? And then I multiply times 4, and that would give me the length of the whole thing. Yeah? All right, so what are we going to need to do this if I'm going to find the length of that blue curve? What am I going to need? I'm going to need the derivative, and I'm going to need to square it. And that's going to look scary at first, but it's actually not going to be bad. So the derivative of this function is 1 over 2 roots of r squared minus x squared. Because the derivative of the square root of anything is 1 over 2 times the square root of that stuff inside. Then, derivative of what's in here. And what's the derivative of what's in there?
Minus 2x.
Remember, r is a constant, right? R is a fixed number here. So what's the derivative of a constant? 0, and then derivative of negative x squared is negative 2x. Yeah? That's times right there. And the 2's cancel, and I still have a negative x on top, and on the bottom I have square root r squared minus x squared, like that. That's f prime. Square it. It looks like things are getting ugly, right? Like, this is somewhat intimidating looking at this. But when you square the bottom, the square root goes away, so that does make us feel better, right? So x squared here, not quite. Two terms can't do it that way. All right, so that's our derivative squared. Let's go to the formula. Arc length is integral, right? Blah, 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 square root 1 plus that thing. So my arc length of that blue piece should be the integral from 0 to the constant r, square root 1 plus x squared over r squared minus x squared dx. That looks pretty bad, but we just learned a lesson in the last problem that when we see complicated integrals like that with roots like this, that one thing that kind of saves the day sometimes is to combine. Common denominator. Put these two together, right? So what must you put here and here? R squared minus x squared, top and bottom. I'm going to go ahead and just throw it in here. R squared minus x squared, r squared minus x squared. That's 1, right? Put the two together, and what happens? Your x squareds cancel. You're just left with an r squared up there, aren't you? Okay, I'm going to have to continue. Clear myself some room here. So the length is equal to integral 0 to r square root, what do you say was left on top? R squared, and on the bottom, r squared minus x squared. Still looking pretty bad, but r is a constant. So let's do the root of the top and bottom separately right now. What's the root of the top? R, right? And r is a constant. Bring it out of the integral. I will have a 1 up here, and then on the bottom I still have the square root of r squared minus x squared dx. So do y'all see what happened with the r? Take the root of it, you get r, pop it out, because it doesn't have an x attached to it. Now this root thing on the bottom I can't pop out because it's got an x in there. Could do trig sub, but I can do even better because that's a direct formula. Arc sine. Remember, tangent is squared, squared, added together, no root. So this one is arc sine. I believe it's formula 16. So the antiderivative of this, remember we have the r out front, the antiderivative of this should be sine inverse of, the formula in your sheet is u over a. In this case, u is really the variable x, so we have x over, and we don't have a here, we're using r. So if you don't have any idea where that came from, I suggest you look at your formula sheet and make sure you can come up with that. This line is going to be integrated from 0 to r, right? We're pretty much there now. First plug in r. R for x. R divided by r? 1. Arc sine of 1. That's asking you at what angle is sine 1? Pi over 2. Okay? So when we plug in r, we get r times pi over 2, right? Minus, then when we plug in 0, 0 over r is 0. Arc sine of 0 is 0. So that zeroes out. So our answer is basically 1/2 pi r. That's the answer. So are we right? Yeah, remember, that was only 1/4 of the circumference. So multiply that by 4, and what do you get? 2 pi. Confetti? No? So we've proven that the circumference of a circle is 2 pi r. All right, good. We've got about 15 minutes. Y'all good? Y'all feeling good? 7.5, surface area. I had a student tell me the other day, it wasn't a student from this class, it was just another, I'll leave them anonymous. They were getting upset with me about how much material I was making them have to learn in this class. And I said, take it to the state of Texas. Don't tell me. State of Texas determines what Cal 2 is. And even at this pace, we're not going to finish the whole course. There's no way we'll make it. So, you know, what's that? We won't get through, we probably won't get to polar coordinates and polar equations. We probably won't. If so, it'll just be like a one-day type thing. But not to worry, because polar coordinates and parametric equations is something that you can pick up very quickly. It's not like techniques of integration where we have to spend several weeks on it because you have to do a bunch of repetition. It's something that you can just okay, yeah, there it is, I get it, no big deal, move on. It really is easier to swallow later. So trust me, I wouldn't leave you hang out to dry like that, leave a whole part of this class out. Some things you can put Band-Aids on, right?
Yeah.
And other things you can't. Polar coordinates is one of those things you can put a Band-Aid on it later. Sequences and series, you can't put a Band-Aid on that. You have to spend time on it. So, all right, surface area. Let's go back. Almost the same problem we just had. You've got this curve sitting here. We just found a way to measure its length. Now what I'm going to do is I'm going to wrap it around the x-axis again. But this time, I'm not wrapping a region around. Remember, when we were wrapping before, we were wrapping an entire region around, and that region was creating a solid, wasn't it? This time, if I just wrap just this curve around, it's going to create this weird shaped, almost like a, I don't know. It's almost like a bell that's kind of been turned sideways and cut the top off. Doesn't that kind of look like a bell? It's hollow, right? I could put my hand in here and it's hollow, except it has this shell shape to it, right? And the question is, what's the surface area? So if I wanted to actually come in here and paint the outside of this, what would the area of that outside be?
So instead of washers, it's the arc length added up.
Yeah, instead of washers, it's like an arc length added up. Very good. But let's see, there's a little bit in there we have to be careful with. So let's go back over here. Let's do an infinitesimal cut. All right, and let's take just this right here and just wrap that little segment around. If we wrap just that little segment around, it would have given us like one little strip of this, wouldn't it have? One little strip? Let's look at that over here, though, without the whole picture. It would just look like one little strip, like this. And it would be hollow. This looks almost like a rubber band, right? Like if I had a rubber band sitting out here. And I want its area. So I'm going to come in here and I'm going to cut it with a pair of scissors. Cut it, and I'm going to lay it out flat. And when I lay it out flat, I get this long, narrow strip, which is a rectangle. And what is the area of that rectangle? That's the question, right? What's the area of this? I'll start with the easier part. What is this length? 2 pi r. But r is actually the distance from here to here, right? Which, if we come back, is actually the distance from here to here. So if this is the function f of x, isn't the radius just f of x? Right? This distance is the same as this distance, and that's f of x. Do you all understand why it's 2 pi times f of x? That picture that we had earlier, where if this goes like this, and I cut it and open it up, then this length was the circumference, wasn't it? So 2 pi times the radius, but the radius is the function's height. That all, I think that's okay, yeah? The width is the part that is tricky. Because your instinct really probably wants to tell you dx. But it's not dx. Dx is the width of this, right? But the width of our rubber band is actually has a slight angle to it, doesn't it? It's actually the length of that little arc piece, right? Because this may be curved here. And so there's actually maybe a little bit of a curvature to the top of that. So we need to account for that. So that little slice right there, this little piece, is actually the arc length. And the formula for the arc length, we just derived it. It was this, 1 plus the function's derivative squared dx. Okay, so it's the circumference of the rubber band times the width of it, but the width of it is the arc length of the rubber band, or the arc length of that little strip. So in terms of a formula, right, with integrals and stuff, is this not going to look a lot like the arc length formula? Don't you think it will? Let's see. See what our formula should look like. You tell me. Maybe you can come up with it. Surface area should be integral. Where to where? I didn't label it on my graph, but a to b, because it's my x, right? So a to b. 2 pi, right? 2 pi is going to pop out because 2 pi is a constant, right? And then we have f of x. That can't pop out because it's a function of x. It has to stay in the integral. And then this, which is the arc length formula, right? So what's in red was arc length, right? If you want surface area after you revolve this around the x-axis, then the only change is a 2 pi out here, and you have to multiply by the function itself also. Now that may make you think like, well, you know, that's terrible because now it's even more complicated. But this actually sometimes saves you. Having this out here gives you something like where you can have like a basic u sub, like a u du or something, and it can be nice. All right, so we just apply the formula. Right, that's what we would do. Someone give you a problem, say what's the surface area? Apply the formula. So I have an opportunity for you, a take-home quiz, all right? And I'm not going to do a single example of this today. I'll pick up maybe next class I'll do an example. But do you all see there's really not a big change to what we just did a second ago? What I am interested in is this. So this is your quiz. Take home, do next time. If you were to take the sine curve and just look at that first arc of the sine curve, just this first arc right here, and rotate that arc around the x-axis, you would get some weird, almost football-shaped thing, right? I don't want to know its volume, okay? I'm not asking you for the volume, because that would be me asking you to take the whole region and wrap it around, right? That's not what I want. I just want the arc wrapped around, hollow inside. What's the surface area? Okay? So surface area, this thing wrapped. That's my three-dimensional picture of it, right? That's my 3D picture. What's the surface area? Question mark. What are you going to need in order to do this? What are you going to need to do? Take the derivative, square it, right? Plug it in here, put the original function out here, and then start cooking up your methods of integration and see if you can figure out how to integrate it. All right, now as far as homework for the other sections, let me, I forgot to write them down and tell you, what it is. So what I'm going to do real quick is I'm going to bring up my lecture from earlier today. And I'm going to see if I can just get to the homework here at the end. Oh, there it is. Okay. I'll write it down again because it's hard to see. But for 7.4, page 391, problems 7, 9, and 15. And then from 7.5, page 397, problems 5, 7, and 11. So there's really like 3 things you should do, well, 4 things you should be doing tonight or before we come in again. Remember, there's an assignment from 7.2, number 38 and 39, which I didn't really cover, which were the cross sections. 7.4, which is arc length. 7.5, which is surface area, which I have not even given you an example of. And then the quiz on surface area, which will be due next time. We come in on Thursday, and we will talk briefly about 7.6, which is applications. And I'll just tell you ahead of time that the applications section, I always feel bad because I want to spend like 3 weeks in the applications section because there's lots of cool stuff in there. But this is not an applications course. So I have to kind of choose, just sign it. I have to kind of choose, sign-in sheets coming around, what I want to show you, and what I think we can go without. I mean, you technically could go without the whole section, but it's nice to see something, these integrals used for something. So the things that I've chosen are things like calculating work done. So like physics, force times displacement is work, so we can compute how much work is done on an object. And then I'm also going to do center of mass and centroids and moments of inertia and things like that. So some physics things. I'm not going to do hydrostatic pressure, which I like that topic too. But so I'm just letting you know, we're going to do 7.6 briefly, couple of topics, and then we're going to move on to chapter 8. Okay? Any questions while the sign-in sheet's going around?
How far away from the next test?
The next test,